everyone. Today we're going to be looking at an example from exercise 1.3 from the jacplus textbook. I'm only going to be doing the first example, which is where we look at the conditions for one solution and, well, no solutions and infinitely many solutions as well. So here we have a picture showing three different situations for simultaneous equations. And what we want to understand is the conditions where we have one solution. So this is one solution here, and you can see that the lines, the pink line and the blue line, are intersecting just once. So this is one solution, and what will always happen here, let's say we've got our equation y equals mx plus c, which is of course an equation of a straight line. What we can say is that the gradient has to be different for the two lines. So it doesn't matter if they're both positive, if they're both negative, or one is positive and one is negative. In this picture where we've got the pink line with a negative gradient and the blue line with a positive gradient, but you could also have a situation where, just say we've got a purple line and it could look like this. That's not a very good line. Try that again. Like this. This would also have a positive gradient, but it intersects a blue line once as well. So as long as the gradients are different, that will give us one solution. The y-intercept, or c value in our equation, that could be anything. They could be the same or they could be different. So for example, with the pink and blue line there, the y-intercepts are different. You can see clearly that, well, the blue one is there and the pink one's there, positive and negative respectively. However, we could have a situation where the line is having its solution, the two lines have their solution where they intersect on the y-intercept. So that would be the same y-intercept. So I'll just say anything for that one there. So this is one solution. If we look at no solutions, so in the second picture here, no solutions, you can probably see quite clearly that the lines are parallel. So that means, of course, that the gradients are the same. And the y-intercept, well, that has to be different because, well, let's look across to where we have infinite solutions here. This is no solutions. So they're two different things, infinite solutions and no solutions. For infinite solutions, what's drawn here is it's the same line, one on top of the other. And you might think, well, that's silly, it's just one line. But as we'll look at down here, you could write the equation in two different ways, two copies of the same line, they're one on top of the other. So in this case, the gradient is the same. And, well, the y-intercept is also the same. So if we go back to no solutions and it's got the same gradient, the y-intercept would have to be different. Because if it was the same, then, well, you'd have infinite solutions again. So these are the representations in pictures. And it's quite good for you to draw those out and understand what conditions make each situation. So look, on this little table down here, this is from Cambridge, we've got an example, case one, where we have two lines and they have a unique solution. So if you were to solve that system of simultaneous equations, you'd find that it has the solution of 3, neg 1. For the second case, well, these are our no solution and they are parallel lines. They're not the same line, but they have the same gradient. So if you were to rearrange those, and look, I will, y equals neg 2x plus 5 and y equals neg 2x plus 7. So we see we have the same gradient, but we have a different y-intercept. And you know what, I will rearrange the first one as well, so you can see that. So the first one would be y equals neg 2x plus 5 and y equals, or neg y equals neg x plus 4, divide everything by negative 1, so of course it will be x minus 4. So you can see in this case we've got different gradient of negative 2 and gradient of 1, of course the secret 1 there, and well, in this case the y-intercepts are different, but if they were the same, who cares, we still would be meeting at just 1 point. Whereas the final one there, we have y equals neg 2x plus 5, and the next one is y equals neg 2x plus 5 as well. So if we rearrange that, we get same gradient and same y-intercept. Okay, so look, let's look at how how we use this information in a question, and this will be the only example I do from this exercise. The others are really just solving systems of simultaneous equations with 3 variables. I feel we don't need a video for that. So find the value of k for which the following simultaneous equations have a unique solution. Now, what I'm going to do it with matrices. So if you haven't done matrices yet, or you're not quite sure of it, I might also show you the other way as well. So what we'll do, I'm going to turn this into a matrix equation. So what that means is I put the things that are in front of the x, k and 4, and then the things in front of the y, which is 3 and 3k. So that's my matrix there, and I'm timesing that by xy, and that's going to equal 1, 0. So just, if you're not quite sure of matrices, we do cover that this year. This is, I think, the superior method. I like this method better. And now what we know is that if we were to solve this system of simultaneous equations, then we would need to undo this because, we'd want to find out what x and y are on their own. And to undo it, we need this thing called the determinant. And the determinant is, I'll call it DT, AD minus BC. And I'm just going to label these things A, B, C, and D. And then we can work out what that would be. So the determinant would be k times 3k minus b times c, which is 3 times 4. So that's going to be 3k squared minus 12. And well, when we use the determinant in our solving for x and y using matrices, what we need is 1 over the determinant. And the point is that you can't divide by 0. So that's a rule in methods you would have learned in year 11. Can't divide by 0. So that means that for the equations to have a solution, the determinant cannot equal 0. So, well, we just do that. 3k squared minus 12, we know cannot equal 0. And then we can just solve and see what k cannot be. So I'm just going to do that. I'm going to add 12 on both sides. 3k squared equals 12. I'm going to divide by 3 on both sides. That gives me k squared. And then, of course, square root both sides. So we get k equals plus or minus 2. So and actually I should say cannot equal these things, not equals. So the point is that to have a unique solution, k can be everything except for -2 and 2. Notice I'm using the squiggle brackets there because -2 and 2, it's not a range of values there, it's just those -2 and 2 on their own. And notice I use this backslash, it doesn't go the other way. So we're saying k cannot be -2 or 2, so that means it's everything except -2 or 2. So that's our answer for one solution, for a unique solution. So any value of k that's not -2 or 2 is going to give you gradients which are different, and that's what you want for a unique solution. I might just take a look at if we would have no solution or infinite solution. The question is only asking us for a unique solution, so that's the end of that. But let's go ahead and look at what happens if we have no solution or infinite solution. And I'm going to sort of do those together. So what we know is that for one solution, k can be -2 or 2. So let's see what happens when k is -2. So actually, I'll do that before I talk about that. So when k equals -2. So let's see what the equations are. kx plus 3y equals 1. So let's at the other one, 4x plus 3ky equals 0. And let's just sub that 2 in, or negative 2 rather, where we see k, and see what we get. See what those lines are. So neg 2x plus 3y equals 1, and 4x minus 6y equals 0. So I can rearrange those to 3y equals 2x plus 1, y equals 2/3, x plus 1/3. So that's one equation. And the second equation is going to be, we're subbing negative 2, yes. So we're going to have 4x, no, sorry, I've already subbed it in. So now I just have to rearrange. This is equation 2 here. So I'm going to get neg 6y equals neg 4x plus 0. And I'm going to get y equals 2/3 x plus 0. And what we see here is that our two equations, equation 1 and equation 2, well, the gradient is the same, but the y-intercept is different. And if we look back to what that means, what that is in terms of our table, different y-intercept, but the same gradient, we're going to get parallel lines. So this is for no solution. So and that must mean, well, the other one, we'll check that out when k equals 2. So let's do that. 2x plus 3y equals 1, and 4x plus 6y equals 0. And let's see what we get for this. So 3y equals neg 2x plus 1, y equals neg 2/3 x plus 1/3. And the next, that's equation 1. Equation 2 is going to be 6y equals neg 4x plus 0. And, well, in this case, we still get no solutions. So if we had got the same y-intercept as well, then that would be infinite solutions, but we don't. So this is actually quite good to see, because I was going to say, well, you know, that must mean the other one is infinite solutions. It must mean k equals 2 is infinite solutions. But in fact, they're both no solutions. So unless the y-intercept and the gradient are the same, it is not infinite. So this is also no solutions. So that gives us an overview of how to do one solution, no solution, and infinitely many solutions. This is relevant for jacplus 1.3, and that is all.